In this chapter, you're going to find that a lot of people, they can kind of get confused by the formulas that we put out there. We initially tell you that momentum, which symbol is P, is equal to that. When you're dealing with changes in momentum, you're looking at a before and after case. So the velocity is what changes, not the mass. So we have a change in momentum, delta P. Delta P is going to be equal to your final momentum, which would be mass times final velocity minus mass times initial velocity. When we introduce the concept of impulse, it's also a fairly complicated concept to understand, because we're told that when forces are applied over time during collisions, it's not the same force over and over again, it's variable. So it grows and then it shrinks over the course of time. Usually this time is very short. We say that if you get this area in here, that's your impulse. The symbol is J. So the area here would give you your impulse, but we also said that J can be calculated by the average force times the time, and the collision time would be however much time that is. When we introduce the impulse momentum theorem, we say, well, when you have changes in momentum, it's because the object experienced some sort of impulse through some sort of force. And we said that J is equal to the change in momentum. So the impulse is equal to the change in momentum. And for convenience, I often like to write it like this. Now, we got to be careful here, because some people kind of forget about this when using this. So let me just kind of give you an example of that. If you have, let's say, an object coming in. It's coming in at 20 meters per second. Let's give it a mass of a half a kilogram, 0.5 kilograms. It's going to hit a wall. And then what's going to do is going to rebound that way. Negative 10 meters per second. There's a change in momentum here. This thing experiences a force. We have enough information just based on this to get the change in momentum. Delta P would be equal to mvf minus mvi. So if we take a look, delta P would equal 0.5 times negative 10 minus 0.5 times 20. Let's see what that ends up working out to. Putting it all in, I get the delta P here, based on these numbers, is negative 15, and the units for momentum are kilograms meters per second. All right, now, looking at that, some people have trouble making sense of what this really means here. That event right there, where the object experiences a force, it also experiences impulse, because that force is going to take time. So there's impulse that occurs right there, and it's likely going to look something like this. It would be a force that grows and shrinks. And if I asked you to calculate J, some people would be like, how? I don't know F, and you know what? I don't know T either. So how am I supposed to do that? Well, the fact that you have the initial speed and the final speed and the mass, that means you have the change in momentum. And that's why I said you can't lose sight of the fact that the impulse momentum theorem is initially written like this. We have delta P. Therefore, we also have J. Since J equals delta P, basically what ends up happening is that our impulse is also equal to negative 15 kilograms times meters per second. Now, had I given you a collision time, then you can start to calculate the force. So let's just say that, okay, this time right here was a very short 0.05 seconds. Once you have that, then you could go and look at this aspect of it and say, let's solve for what that force is. So if I said J equals the average force times the collision time, well, now I know that J is negative 15, and my force is unknown, and the collision time is 0.05 seconds. So negative 15 divided by 0.05 gives me the average force, which would be equal to negative 300 newtons, which makes physical sense to me because if I'm looking at that negative sign, that force is to the left, and now I have my force. All right, so it's very important you recognize that you don't need to have the force or the time to calculate J. All you need to know is the initial speed and the final speed and the mass. You can get the change in momentum, and then you can get J. And you can start to analyze what makes up J if you have that other information. All right, so that's something people often overlook in this unit. And on that sheet that I posted for you, I think you'll run into a little bit of that, so hopefully this will help you out.